Hello everyone, and welcome to this video on the Cauchy-Schwarz inequality. In this video, I'm just going to first start off by stating the Cauchy-Schwarz inequality for any inner product space, and not going to go into a proof of it. That's not the point of this video. I'm just going to go over after that just several examples where I'm asked to verify that the Cauchy-Schwarz inequality indeed holds for some pair of given vectors from and under a certain inner product. Okay, so here it is, the Cauchy-Schwarz inequality, and it states the following: any two vectors, say u and v, in an inner product space V, right? Now remember what an inner product space is, right? It's a vector space that also has a well-defined inner product, right? And an inner product was, this wedge. It was denoted by this wedge form around a pair of vectors, and it satisfied certain properties as well, right? Remember, inner product was symmetric, additive, had a homogeneity property, and also positive definiteness. But I'm not getting into that. I've had another video prior to this where I talked about verifying that a certain function is an inner product. So not going to do that here. So any two vectors u and v in an inner product space called, say, V, capital V, will satisfy the following inequality. So if I were to take the inner product of vectors u and v and square that number, this result will always be either less than or equal to the inner product of u with itself multiplied by the inner product of vector v with itself. Right. And if you were to take the square root of both sides, this would be equivalent to saying that the absolute value of the inner product of u with v will always be less than or equal to the the non-negative square root of the inner product of u with itself multiplied by the inner product of v with itself, right? All under the square root. So I'm just going to verify this first statement. These two statements are saying the same thing. And I'll come back to this second statement in a future video when we talk about norms, right? Things called norms, which are tantamount to magnitude, length. You'll see in a future video of mine on norms in an inner product space. Okay, so now that I've got this out here, this stated, let's just verify that it works for certain examples. So that's all I have for the rest of the video, just a few examples where I'm asked to do the following, and I have the same instructions for the rest of the video. Verify that the Cauchy-Schwarz inequality holds, for the given vectors and inner products. All right. So in this particular example, u and v come from vector space R2, and when I say vector space, I'm going to and I don't mention definitions of vector addition or scalar multiplication. We are going to assume the standard definition for vector addition and scalar multiplication in that particular vector space. So it's a Euclidean space R2, and say vector u in this example is the vector 5, 12. Vector v is the vector with components 3 and 4. And this, to make it an inner product space, right? R2. I've got this inner product. Again, I'm not going to verify that it's an inner product. We're just going to assume. I'm giving you an inner product here, something that does satisfy those 4 inner product axioms. The inner product of two vectors u and v is the dot product, right? Or the Euclidean inner product, or standard inner product of u and v. All right. So I'll write this up at the beginning of every example. here it is again. Now I'll just put CSI, right? Cauchy Schwarz Inequality. Not really, haven't seen the shows, right? That has nothing to do with crime scene investigation. Right? Cauchy Schwarz Inequality. So here it was again. The Cauchy Schwarz Inequality, CSI. The inner product of u with v squared should be, will be, less than or equal to the inner product of u with itself multiplied by the inner product of v with itself. So let me just find these three things and see that they are this is indeed true for this, on this these two vectors in this inner product space. All right, so first, what is the inner product of vector u there with vector v? Remember, I just said up here that's simply u dot v, right, the dot product or Euclidean inner product, and the dot product of vectors in R2 or any Euclidean space is very simple, right? You just multiply the corresponding components and then added those products, right? So 5 times 3, multiply the first components, and then add to that the product of the second components, 12 times 4, and that's 15 plus 48, 63, right? 15 plus 48, 63. Okay, and then we're going to be squaring that in a second. Which, yeah. Next, the other side, right? Before I go into verifying, what's the dot product of u with u, or the inner product of u with itself? Again, here that would be u dot u. So that's u with itself. So 5 squared, 5 times 5 plus 12 squared, 12 times 12, that's 25 plus 144, that's 169. Okay. And then finally, the other thing before I plug in and see if it's working, the inner product of vector v with itself, or v dot v, is 3 squared plus 4 squared. 3 times 3 plus 4 times 4. 9 plus 16, 25. All right. So let's square the inner product of u with v. All right, so the inner product of u with v, squared, is 63 squared. And sorry, I'm not the, probably should be able to do this mentally, but let's do it real quick on the calculator here. All right, so 63 squared, 3,969. 3,969. And then let's take a look at, on the other side here, and see if this is indeed less than or equal to, inner product of u with u multiplied by the inner product of v with v. So what is the inner product of u with itself multiplied by the inner product of v with itself? We saw that the inner product of u with itself was 169, multiplied by the inner product of v with itself was 25. Again, I mean, since it's multiplying by 25, I should be able to do this in my mind, but it's late. Alright, so 169 times 25, 4,225. And look, this first quantity I found is indeed less than this second quantity I found. So the less than part is holding true here. So we indeed have verified Cauchy-Schwarz inequality, right? So we see that the inner product of u with v squared is actually just less than, in this case, the inner product of u with itself multiplied the inner product of v with itself. And if it's less than, it's surely less than or equal to. So yes, right. CSI holds, right? The Cauchy-Schwarz inequality holds. Wonderful, and it should, right? If you have a properly defined inner product, like the dot product is, on a vector space, you know, this CSI, right? This inequality, Cauchy-Schwarz inequality, should be true, and it will be true if you have a proper inner product defined, right? Okay. All right. So my next example, right, that one involved the dot product, right? But that's not the only example of an inner product on some vector space, as you've seen in previous videos, hopefully, of mine or somewhere else. So here's another one. Now suppose my vectors this time are matrices, right, instead of vectors from R2 like in my last example. So I have, say, A and B are, 2 by 2 matrices. They belong to that vector space of 2 by 2 matrices under, the standard matrix addition, standard scalar multiplication. And suppose matrix A, the first, vector, is this 2 by 2 matrix with rows 0, 1, and 2, -1. And matrix B is another, 2 by 2 matrix, another vector with rows 1, 1, and 2, -2. And again, this is another inner product that has been verified in a previous video of mine. Right? This is a proper inner product, that Frobenius inner product, which is kind of like the dot product, where you take the two matrices and you just multiply the corresponding entries. So I'd do the first row, first column entries, multiply the first row, second column entries, second row, first column, and second row, second column. You multiply corresponding entries and then add them up. Now, if you've practiced this enough, you've probably noticed that the Frobenius inner product is equivalent to the trace of A transpose times B. If I were to take A transpose, multiply it by B, and then just take the trace of that product. Now remember, the trace of a matrix, a square matrix, was the sum of the entries down the main diagonal. Well, if I took the transpose of A multiplied by B, the entries down the main diagonal would be 0 times 1 plus 1 times 2 for the first row, first column, plus, and then 2 times 1 plus -1 times -2. And it's exactly, adding those together gives you exactly what the Frobenius inner product is, okay? All right, so that is a proper inner product. So this R2 by 2 space with this inner product, right, is an inner product space. So, being a true inner product space, the Cauchy-Schwarz inequality should hold. So again, CSI Cauchy-Schwarz inequality. And I'll write it here with involving, my vectors, my matrices A and B. So what the CSI states, what the Cauchy-Schwarz inequality states, is that the inner product of A with B squared will be less than or equal to the inner product of, A with itself multiplied by the inner product of B with itself. All right, and let's test these. All right, so first I'll do the inner. What's the inner product of A with B? All right, so like I said, you could find what A transpose times B is, and then do the trace, right? The sum of the main diagonal entries of A transpose times B. But again, this is just going to wind up being the same as the Frobenius inner product. So 0 times, I'll write it out. 0 times 1, those are the first row, first column entries, plus 1 times 1, the first row, second column entries, plus 2 times 2, the second row, first column entries, plus -1 times -2, the second row, second column entries, right? And this is equivalent to 0 plus 1 plus 4, so 5, and then plus another 2, so that's 7, right? And when we square that, that'll be 49. All right, and then what's the over here? I want to find these two as well. These two, all the inner products. What's the inner product of A with itself? All right, so this is simply each entry squared, right? 0 squared, added up, right? 0 squared plus 1 squared plus 2 squared plus, -1 squared. this is 0 plus 1 plus 4, that's 5, plus 1 is 6, right? And then what is the inner product, this inner product, right, of B with itself? And again, that's just the entries of B all squared and added up, right? So 1 squared plus 1 squared plus 2 squared plus -2 squared. So I have 1 plus 1 is 2, plus 4 is 6, plus another 4, right, is 10. And we do see, right, that the inner product of A with B squared, right, the inner product of A with B squared is 7 squared. That's 49. And because this is a proper inner product space, right, R2 by 2 with this inner product, this should be less than or equal to the product of the inner product, the product of the inner product of A with A and the inner product of B with B. And let's see, the inner product of A with A multiplied the inner product by the inner product of B with itself is 6 times 10, or 60, and indeed we are seeing that this is less than this again, right? So less than or equal to for certain. Right. So we are seeing, right, the inner product of A with B squared is indeed less, and if it's less than, it's definitely less than or equal to the inner product of A with A multiplied by the inner product of B with B. Right. The CSI, the Cauchy-Schwarz inequality holds, as it should for any pair of vectors in an inner product space. Okay. So again, some pretty simple stuff to show, right? All I'm doing is verifying that the inequality holds, right? We're given a proper inner product space and a couple vectors, and just running through those inner products and making sure that the inequality is true. Alright, so I have just one last one of these, right? There's tons of examples out there. You could actually think of, there's infinitely many inner product spaces out there, inner products on some vector spaces you've seen. So I'm not going to go through too many. I think a few examples is plenty here to demonstrate what I'm trying to show every time. Alright, so here this time, instead of my vectors being vectors from R2 or vectors that are matrices, here my vectors are going to be some functions, f of x and g of x, that are continuous on the interval from 0 to pi over 4, the closed interval from 0 to pi over 4 on the real number line. Alright, so this time my vectors are functions that are continuous on this closed interval. Remember, that's what this c with the interval from 0 to pi over 4 meant, right? This was the vector space of all continuous functions on the closed interval from 0 to pi over 4, using standard function addition and scalar multiplication. So my vectors this time are, say f of x is sine of x, right? That's a continuous function on this interval. G of x equals cosine of x. That's also a continuous function on this interval. So both of these are vectors in this vector space, and this is that integral inner product that I had discussed again in a previous video on inner products. This is a proper inner product, satisfies all 4 of the inner product axioms. The inner product of functions f and g is the integral over this interval, the definite integral from 0 to pi over 4 of the product of f and g with respect to x, right? F of x times g of x dx. Alright, so some calculus stuff here. Okay, so again, I'll write out what the Cauchy-Schwarz, this is right, this c over, this c with the 0 to pi over 4 interval, this vector space with this inner product is an inner product space. So for any 2 functions in this space, the Cauchy-Schwarz inequality will hold, should hold. That is, the inner product of function f with function g squared should be less than or equal to, and it will be, the inner product of function f with itself multiplied by the inner product of function g with itself. All right, so let's see. So what is the inner product of f with g in this particular example? So that's the integral from 0 to pi over 4 of f times g, all right, with respect to x. So sine of x times the cosine of x dx. All right, now this could be done in a couple ways here, right? You could use u substitution, right? Let u be sine x, and then this would just be u du. And then the integral would be half u squared, and then you replace u with sine x again. So I could get, half of sine squared of x, and then we're evaluating this from 0 to pi over 4. And you can double check, take the derivative of this, right? Don't forget the chain rule, and the derivative of this function here would be sine x times cosine x. Another thing you could have done was, this sine x times cosine x, right, using your trig identities. Sine x multiplied by cosine x is half of the sine of 2x, right? Half of the sine of 2x, and then you could have gone from there. But I've got a proper antiderivative right here, so I'm just going to use this. So remember, you plug in the upper limit first. Now the sine of pi over 4 was the square root of a half, right? The square root of 2 over 2. So I'm squaring that, so this is a half times a half, right? When I plug in pi over 4, it's a half times a half, right? The square root of 2 over 2 squared, 2/4 or a half. And then the sine of 0 was 0. So this is a quarter. This is 1/4, half times a half that I have here. All right, and then we're going to square that in a minute, right? When I do the inner product of f with g, square that'll be 1/16. All right, now what about the inner product of f with itself? Okay, so this would be the integral from 0 to pi over 4 of f with sine. So sine times sine, sine squared with respect to x. All right. So if you recall, there was a nice little power reducing formula here. This would be the integral from 0 to pi over 4. And sine squared was half of, and I'm going to pull that half out, right? You pull constant factors out. Was half of the quantity 1 minus the cosine of 2x. Right, 1 minus the cosine of 2x, and then with respect to x. All right, and then we integrate this. Right, so I got the half out here still, and antiderivative of 1 would just be x, minus cosine 2x would be minus half of the sine of 2x. When I do antiderivative, we're evaluating from 0 to pi over 4. Right. Yeah. And then I plug in pi over 4. Now, when I plug in 0, right, you have 0 minus 0 here, so that's nothing. So all I'm going to get anything out of is plugging in pi over 4. So this is half of pi over 4 minus half of, the sine of pi over 2, which was 1. Right, pi over 4, plug in pi over 4 for x, that's 2 pi over 4, that's pi over 2. Sine of pi over 2 was 1. So just minus a half. And, if I want to, I guess I could distribute the half here. This is pi over 8 minus a quarter. Right, pi over 8 minus a quarter. And then we'll have something pretty similar to this when we do the inner product of g with g. Inner product of g with g and the integral from 0 to pi over 4. Now g was the cosine of x right up here. So it's cosine times cosine, or cosine squared. And as with the sine squared, remember there was this power reducing formula. That's going to pull in the half out here. You know, the cosine of x, the cosine squared of x was half of the quantity 1 plus the cosine of 2x with respect to x. Right. Okay. And then, take the antiderivative, 1/2, and then again you have x here, and then this would be, plus 1/2 times the sine of 2x. And then we're evaluating from 0 to pi over 4. And just as before, when I plug in 0, this will be nothing, so I'm just going to be popping in pi over 4 here. So this is half of, pi over 4 for x will be pi over 4, and then again plus 1/2, right? Plus 1/2. And distributing the half here gives me pi over 8. Pi over 8 plus 1/4. Alright, now let's test it out. Pop these in, see if the inner product of f with g squared is indeed less than or equal to the product of, the inner product of f with f and g with g. Alright, so what is the inner product? Cover that up for a second. What is the inner product of f with g squared? Well, that's 1/4 squared. So that's 1/16, right? 1/4 times 1/4. And the inner product of f with f multiplied by the inner product of g with g, well, that's the product of two conjugates. You can see that's pi over 8 minus 1/4. I'll write it out. That's pi over 8 minus 1/4 times pi over 8 plus 1/4. Product of two binomial conjugates is a difference of squares, right? So this is pi squared over 64, right? Pi over 8 squared. And then minus 1/4 squared, minus 1/64. 16th, not 64. 1/4 squared, 1/16. All right. Now, you could try, comparing these. I'm just going to punch in the calculator. All right. You could try setting up comparisons with these, but like I said, I'm just gonna do this. So what is pi squared divided by 64 and then minus 1/16? Alright, and then what is 1/16? Alright, so this 1/16, right, the inner product of f with g squared, 1/16 is, well, it's actually equal to, not approximately equal to. It ends, right, 0.0625. This inner product of f with f times g with g, the pi squared over 64 minus 1/16, is approximately, 0.09 something, 0.09 I'll say, but you can see it's small, it's larger than 0.06 something, right? 0.09 something. They're larger in the hundredths place. So the Cauchy, Cauchy-Schwarz inequality, that CSI is holding again, as it should, right? For any pair of vectors in an inner product space, right? So we are seeing that the inner product of f with g squared is less than, again it is less than or equal to the inner product of f with f times the inner product of G with G. Now you will come across some cases where they're equal, right? Especially if they're the same. Basically, if the one of those cases would be if they're the same vector, right? If you have the inner product of f with f squared, well, that's definitely equal to the inner product of f with f times the inner product of f with f. Right? So you will come across some cases, where it's not always less than, as in my first three examples here, but where there's the equality part holds as well. Okay, so. And if you wanted to punch these integrals in your calculator, fine. I mean, like I just did it by hand here because I was, just wanted to do some calculus work for you. Hopefully, refresh your memory on some trig identities, some trigonometric integration. But, yeah, if you use a calculator, that'd be fine as well. All I'm trying to do is verify that one quantity is less than or equal to another quantity for each of these examples. Okay, so get this in your mind. Right, get this in your head. The Cauchy Schwarz inequality. In fact, I'll finish my little talk here with the page with this up again. Very important result in mathematics, regarding inner product spaces and inner products. Right. So I definitely would recommend memorizing this, especially if you're in some linear algebra course, right, going forward. Okay. And as I mentioned, we'll get to taking the square root of both sides of this and looking at this result down here in a video coming up. So, hope you enjoy practicing problems like this, and thank you very much for watching.